This is No Nonsense A-Level Physics Lesson 56, all about work and energy. Yes, this marks the beginning of a new topic, work, energy and power. Very short topic, so let's get into it. The first thing is a revision of some GCSE level ideas. When we talk about work and energy, we talk about energy stores and energy transfers, which some people I've heard call energy pathways, but I'm not a fan of that particular terminology. So let's break our page into two for stores and pathways. Let's start with energy stores. So there are 5 energy stores that you needed to know for GCSE level, and we can add to that as well, but let's just start there. Bit of a reminder. We had the gravitational potential energy store, gravitational potential energy. And so that is a store of energy which is associated with the position of some sort of mass, some body with mass in a gravitational field. We have the kinetic energy store, and that is associated with the movement of the body. We also had the elastic, and it sometimes was called elastic potential energy store. I'd prefer to just call it elastic energy, but okay, I suppose you can have an elastic field. So elastic potential energy, that's the terminology we used at GCSE level. We also had thermal energy. Thermal energy stores, and we had chemical energy stores. Now there are others we can add to this list. So we could add to this list, I'll use a lighter green for this, we could add to this list the idea of electric potential energy. And we'll be dealing with that in year 13. We could add to this list the idea of nuclear potential energy. I guess I'll call it that for want of a better word. The energy stored in the nucleus of atoms due to the strong nuclear force. We could even have energy stored due to pressurized containers. So we can have a pressurized gas store of energy. I don't know what else we'd call it. It doesn't have a nice snappy name. It's not elastic potential energy, it's something different. It's not because of the container's elastic potential energy. It's actually in the gas itself, because the gas is pressurized. And there's bound to be more. I haven't mentioned magnetic potential energy, whatever that would be. And there's bound to be more I haven't included. But you'll notice what's not included on that list is light energy, is sound energy. These are not energy stores. So energy stores, we put energy in these stores, but there is only energy. There isn't different types of energy, which was an older model, used to be taught as types of energy back in the 80s and in the 90s and before that. But in around about the year 2000, their fashion changed and we started teaching about energy stores instead. The problem with energy types is that some young people assume that there are different energies. Energy transforms in some way from one thing to another. That's not really how it is at all. When we look at energy conservation, it is far more useful to visualize a single substance, a fluid called energy, moving around in stores. Now that's still not perfect as a model, because of course energy isn't a substance, it isn't a fluid, but it's seemed to be a better model, so that's what we teach. And how do we move energy from one of these stores to another? How do we get energy to go from the gravitational potential energy store into the kinetic energy store, for example, or from the chemical energy store to the elastic potential energy store? I mean, probably not in one step in that example. Well, we use 4 different mechanisms. There's energy transfer by forces, so mechanical energy transfer. So mechanical, that means using forces. Forces can transfer energy from one store to another. We also have energy can be transferred by an electric current. Electric current. Now that's a little bit more complicated, and we'll talk about electric currents in one of the later topics when we introduce electricity. But we don't have electrical energy anymore, but a current can be used to transfer energy from one store to another. We have waves, any sort of waves. So by transfer by waves, we've already looked at waves as a topic, but this would be light, electromagnetic waves. This could be sound, vibrations in the air, that sort of thing, can all transfer energy like that. The last thing that can be used to transfer energy is, we could call it heating, but I prefer to call it conductive heating. Radiative heating is waves, it's infrared radiation. So let's call it conductive heating. Convective transfer, convection, is a mechanical issue. It's physically moving the less dense, higher temperature fluid. Now there are going to be other transfer mechanisms. So we've talked about an electric current, but a current of anything. So you could have neutral currents for Z0 bosons, or you could have gluon interactions. Any sort of interactions can transfer energy. We haven't even talked about some of the more esoteric, cosmology yet. Talked about the accelerated expansion of the universe and so on and so on. So this model has a lot of scope to be expanded. But we use the transfers to move energy from one store to another. So electric current is not a store. It's not, it's the kinetic energy of the electrons, although I guess it kind of is. Because you don't need electrons to transfer energy from one place to another. The electrons don't have to travel that whole distance. Right, okay, anything else we need to talk about here? Conservation of energy, so we could say energy is conserved. What we mean by that in a closed system, we've already talked about a closed system, what that means. That's where energy can't be transferred in and out, and then we're saying energy is conserved in a closed system. Sounds like circular reasoning. Noether's theorem is quite difficult to understand what energy is. Energy just becomes an accounting system to check the time symmetry. It's a number that happens to be the same as we do a time translation, but I'm not going to go into that in an A level. So I'm just going to say energy is conserved in a closed system and leave it at that. Principle of conservation of energy. We could also say energy is measured in joules, but we'll come to that in a second. So there are 3 things we need to look at in this lesson. The first one was a bit of a reminder of GCSE. We'd have spent a whole lesson on that at GCSE. We're now going to move on to work. So work done is what we call the transfer of energy from one store to another. Work done is the transfer of energy. So what we used to call transfers, we can now call work. Work can be done by waves, work can be done by electric current, work can be done by conductive heating, work can be done by forces. And we are going to focus on forces doing work during this lesson. So work is done. And the amount of work that's done is the amount of energy that's transferred. Work is energy, energy is work. Work is the energy that is transferred. Now, whether the work is done on an object or by an object determines whether the energy is going into the object or out of the object. If work is done by an object, then it loses energy from one of its stores. Usually it's kinetic energy store. If energy is being done on an object, then energy goes into a store. Usually it's kinetic energy store. Now, I don't think it's helpful in A-level to get bogged down on the work done by or work done on question. And I have not seen yet a situation where students could risk losing marks by getting that mixed up in their heads, whether it's on or by. I tend to just park that to one side. It's useful if you're looking at doing university level physics, but at the moment, just knowing that work is done is enough. Knowing whether it's done on or by is less important. And you say work's done by forces and things, so it can get very complicated indeed. Now, at GCSE level, the amount of work that was done was written as the force multiplied by the displacement. And it may well be that your teacher did not write it quite like this, but this is how I write it. As a matter of fact, I tend to put the S and the F the other way around. It doesn't actually matter in this case. So that is usually how it is written. Sometimes it will be written at GCSE level as force times the distance moved in the direction of the force. But distance in a particular direction is displacement. So why not call it displacement? So F dot S. Now that is shorthand. That is what's called a scalar product. And it is a shorthand. This is a scalar product. And that is shorthand for the magnitude of F multiplied by the magnitude of S multiplied by the cosine of the angle between. Is it the cosine? Yes, it is the cosine of the angle between F and S. I always have to not second guess, but I always have to think carefully because I don't want to mess it up. So let's use that notation there, subscript Fs, to indicate the angle between F and S. Now that's a scalar. It returns a scalar, but that cosine is really, really important. Why is that really important? Because if we've got a situation where an object, maybe it's, let's take a hovercraft or a boat or something on water. Water's quite a convenient thing to use in these sorts of questions. So there's a boat, and let's say that it is being displaced along this direction here. So let's get my straight line tool out and say it's being displaced along this direction there. That's the displacement S. But let's say a force is acting on it, and maybe the force is the force of the wind, which is in this direction here, for example. Now I have to use a different arrow so I don't have the same arrowhead on the same diagram for things that are dimensionally different. We don't want to do that. So there's our force, like that. Well, what's the work being done by that force? What's the energy being transferred by that force? This is the angle, and in this direction it's the angle between F and S, like this. So we'd use this equation to say the work done would be equal to magnitude of S times F times the magnitude of S times the cosine of the angle between F and S. And that would give us our amount of work that's being done by that force. Now, it could be that there's another force doing the same amount of work on the object as there is another force in the opposite direction, so that the total amount of energy transferred is zero. The net energy transfer is zero. For example, if I've got a car driving along, and we could have the force of friction from the road pushing the car forward. That's how wheels of a car work. And that's actually equal in magnitude, that force, to the air resistance force on the car. Well, the resultant force is 0. Fine. You can calculate the amount of work that's done on the car because of air resistance, and you can, well, because of friction and the work done by the car against the air resistance, and those two amounts of energy will be the same because the car will be displaced a certain amount regardless of what forces we happen to be looking at, and so we could work out the same amount of energy going into the car be coming out of the car if the car is travelling at a constant speed. So if, however, there is no force balancing this, then that would be equal to a change in kinetic energy. So we could say something like that, a change in kinetic energy. Remember, E equals half mv squared is the kinetic energy equation, and the m doesn't change and the half doesn't change, so I might as well put the delta before the v. Right, so that is the work done equation. We must include the cosine theta, where theta is the angle between the two vectors for force and displacement. If the two vectors are 90 degrees to each other, then the force is doing no work. As simple as that. And we could take it a step further and we could talk about rate of doing work and power, but that does come up later. So I'll talk about power in a later lesson. The next thing I'm going to say is this equation only works if our force is constant, this equation. If the force depends on where the boat is, so the force is a variable force, then actually we could say that the work done is equal to the integral of the force as a function of the displacement multiplied by ds. And of course, because s is a vector and f is a vector, it would be dot ds. So we'd end up with something that looks a little bit like this. And that's a little bit more complicated, but it does lead us into the last part of this. So this is better, but not necessary for A level. I'll say better, but generally not needed for A level. Not needed for A level physics, because you will have to use calculus in your A level mathematics, and this is a better way of writing what work is being done. Why is that important? Because remember that integration, well, if you're hearing integration and differentiation and all these terms about calculus, and you have no idea what calculus is, I have got a video series on YouTube where I talk about calculus. I derive the important physics equations using calculus, and it's really worth watching if you're studying A-level physics. It's calculus for physicists, or I think that's what it's called. I'll try and remember to link to it, but I tend to forget. So if there's no there's no link to it in the description of this video, then drop a comment and ask. I do pick up the comments on the YouTube videos, and I will add it on if I get reminded. So here we are, F and S. S is displacement, F is force. And if we have a very simple situation where we have a force that is constant, like this, in fact, I don't want to label it with just letters. I really don't like labeling just letters. Force, and S would be displacement. S is displacement because it's from the Latin spatium. Displacement. An interval in a spatial dimension. P, by the way, for momentum, we use a P because it's from patere, which is where we derive, etymologically, where we derive the word impetus and therefore impulse from. So P is from impulse. That's why we call it P for momentum. Anyway, there's our S. There's our F. And so the area here, this area here, that area is equal to the work done. Now that is true for a situation where we have a constant force, like we can see here. But what if we don't have a constant force? What if the force is changing? Well, if the force is changing, then we still have to calculate the area, or at least we still have to determine what the area is, but it won't be a simple, well, not necessarily be a simple geometric calculation. So let's take a simple example to start us off. We'll work our way up towards something more complicated. So in this case, work done is just equal to F times S. Now let's look at the second case. And let's say we've got a force that's increasing like that. Nice and regular increase of force. We have some displacement S like this. And when that happens, we get our maximum force. Just go across like this. We get a maximum force, which I'm going to call F. Now, in this case, the area is this area here. That's a triangle. So everyone remembers the area of a triangle. Area still equals work done. That hasn't changed. But now the equation is the equation for the area of a triangle. So that means the work done is going to be half times F times S. Now that's interesting. GCSE, work done was just force times displacement. Now work done might be half times F times S. And of course, this is assuming that the force and the displacement are in the same direction. So we should put in here a cosine theta and a cosine theta as well. So there's half. Now that's interesting. But what if we have an even more exotic situation? What if instead of having a nice regular triangle like that, our graph is some sort of Gaussian distribution? Actually, no, you can solve a Gaussian distribution analytically. Let's take something that we've measured. We've done an experiment. We've got out our force measuring device, that data logger that measures forces. And we're going to do this. We're going to do an experiment to measure what the force is at some instant. Maybe we're doing the collision thing from a few lessons ago. And we end up with something that looks like that. Something weird. A weird shape like that. We think, well, goodness me, what's the equation for that? Because one approach is to work out the equation of that function and then integrate that function with respect to S to get W. That would calculate the amount of energy transferred. That would calculate the work done. But we don't have time to do that in our A-level physics exam. So how do we get the area under this shape? The area is still work done. How do we figure that out? We count the squares. So we count squares and then we multiply by work done represented by 1 square. That's what we do. Now, in that case, any part square counts as half a square. Now, different exam boards do it different ways, and some exam boards will say if it's less than half a square, it's 0 squares. If it's more than half a square, it's 1 square. You can see they should average out, but this is just a way of approximating, let's say estimating the amount of work that's done in this interesting situation. There is another way, of course, of working out the area, which is to work out the whole area of a piece of paper, weigh it, and then cut out this shape and weigh this shape, and you'll get the ratio of those weights will be the same as the ratio of these areas. So you can do it that way as well, which is quite an older way of mechanically integrating with a big scale, a big balance. Anyway, we're not going to go into calculus at this stage. This is just what it is. And so what equation you choose to use depends on the situation. If you're looking at something like this, where you are stretching a spring, then that is actually Hooke's law. And the equation for the work done on a spring is force times the displacement of the spring times by a half. That's a half F times S. So you can see that is just energy stored in a spring within Hooke's law. In fact, let's write that down in this. This is, in that case, theta would be equal to 0. So cosine theta would be 1. This is energy stored in a spring. So this is elastic potential energy from Hooke's law. So that is actually the same thing, and that's where the half comes from for Hooke's law. And we can do the same thing for kinetic energy as well. But we'll leave that there. We'll move on to kinetic energy next lesson. Hopefully you found that helpful, and I hope I'll see you in the next lesson. Bye-bye.